Alrighty friends, so we're going to talk about compound stoichiometry. We're starting our stoichiometry unit and we're starting with the basics of compound stoichiometry. There are two versions of stoichiometry we're going to be doing in here. It's compound and reaction. So we got to make sure we build good practices now when we're talking about the easier things to deal with. So when we're talking about stoichiometry is all about the methods of conversion. They're methods of conversion. So stoichiometry is a method that allows us to convert between equivalent units of measure. So they have to be talking about apples to apples here. You can't be comparing apples and oranges. And we do this conversion factor idea all the time. You just don't know it's called a stoichiometric conversion. That part you're not aware of, but we'll fix it. So the process goes, if I ask you for a case of soda, how many cans would you expect to bring home? On average, it's 12 cans. Same thing, if I say you have 1 day to do this homework assignment, how many hours is that? You got 24 hours. And if mom tells you to grab a dozen eggs, she's expecting you to bring home 12 eggs. And if you have all year to get save up for your car, you have 365 days. Capiche? Those are the ideas of conversion factors. And this process I'm talking about is what you have to go through. I know lots of y'all can do this through algebra that you learned back in your other math classes, but this process sets you up to be successful when we do reaction stoke and further chemistries. So you need to start being familiar with the idea of building conversion factors. So we have to start our units off by building conversion factors that things can cancel. Because if we got to turn in from one thing to the next, to convert from one thing to the next, or one thing to the next, one thing to the next, you have to be able to find equivalent factors to cancel out units. So if I want to go from here to here, I have to have some kind of unit conversion, okay? And that's what we're going to be talking about. So if you have to solve this through the stoichiometric process, you build these factors. And these factors will look something like this. So you always start with what you're given. You start with what you're given. So in this problem, if you have 736 cans of soda, I'm asking you for how many cases will that produce you? How many cases? And I'm given you have that many cans. So I'm going from cans to cases here. Oh, no, not that. Bloop. I'm going from cans to cases. And if I keep it going from cans to cases, you always start off with your given cans. That's not how you spell cans, Hunter. There we go. Cans. Now I'm asked to go to cases. I know that in one case of soda, I have 12 cans of soda. And now that I have built my conversion factors, I gotta see what's on top can cancel with what's on bottom. That's the goal here. We're looking to cancel out some units. Whereas these... Oops. I need another color. Well, our unit here is cans. That's what we're trying to cancel. And it looks like I have it. So if cans are on top and I got cans on bottom, that cancels because, 2 over 2 is 1. So can over can goes away. And what I'm left with is my goal of cases, because my question's asking me to calculate cases. So I know I'm in cases, so that means I'm done converting. My last conversion factor has my correct unit up top. All right? So now all I do is I multiply the top multiply the bottom, divide the 2. So what I'm looking at here is I'm talking about multiply the top, multiply everything at the bottom. So remember, everything has that invisible 1. So that's 12. I'm left in cases here. Then I divide between the 2. So let me get my handy dandy calculator here. Doop. So I'm going to do 736 times 1 will, of course, give me that 736 again. Divide that by 12. I get 63.3333 repeating cases. However, comma, I need to figure out what sig fig value to use. Sig figs are back again. You look at what you're given to always establish your significant figures. So I should report, I see 1, 2, 3 sig figs there. I'm going to report 3 sig figs in my final answer. So I have 61.3 approximately cases. Ta-da! You did your first stoichiometric conversion. But notice something special. I have number, unit, and I have 61.3 cases of what? Cases of what? Of soda. That's my substance. In stoichiometry, your answer should always be framed as number, unit, substance. You must always give me number, unit, substance for full credit. You're missing a piece, you won't get full credit. Particularly if your number is wrong, the question's wrong. So make sure you have that detailed approach on number, unit, substance, always. It helps to write them in your conversion factors. So let's do it again. If you have 154 cases of soda, how many cans do you have? So here I'm going from cases to cans. Start with what you're given. I have 154 cases of soda. And I know I got to go to cans. All right, so I know I'm trying to get for cases to go away, so case is going to have to go on the bottom. And in 1 case of soda, I have 12 cans of soda. I'm in cans. I know that if they're on the top and bottom, they cancel, so cases of soda go away. Cases go away. All right, so I'm in cans of soda. So now I just do the math. Here we go. 154 times 12 gives me that. And of course, we can't forget about our bottom, but we're dividing by 1, so it doesn't really do anything. That's going to be that 1848 cans. But how many sig figs do I got? I see 1, 2, 3. So you're looking at approximately 1,850 cans, just to keep things consistent, of soda. And remember, I see number, unit, substance. Always. Final answers include number, unit, substance, always. Number, unit, substance, always. Don't forget it. Don't get lazy. So that's the basis of stoichiometry here. And to do stoichiometry, you need to have neat work and have a kind of roadmap. The roadmap is as follows. This right here is called the molar highway. And on the highway, we must stay on the road. To be on the highway, you must stay on the road, which means there are no side streets, back roads, back alleys, underground tunnels, or what have you. So you must stay on your roads. These are your roads. What you cannot do is go from here to here. That's a no-no. We do not do that. You go from here to here to here. You stay on the road. For me to go from here to here, that's one-step stoichiometry conversions. For me to go from here to here to here, that's two-step conversions. Notice my steps. 1, 2, 1. Okay? And in doing these conversions, you have 3 different options to convert between a mass value, particle associations, or some volume units. These volume units have to be at what we call standard temperature and pressure, or STP. This standard temperature and pressure is the standard value in places that chemists conduct experiments. These experiments happen usually around room temperature unless noted otherwise, and at 1 atmosphere, or basically at sea level. We're not doing these experiments or discoveries at the top of Mount Everest or somewhere where the amount of air pressure can influence our products. So let's take it one step at a time here. If we're going from moles to mass, from moles to mass, I know I have to have some kind of gram calculation. Your number of grams comes from what we call a molar mass calculation. That molar mass calculation. I'll show you how to do that in just a second. But if we're going from moles to particles, we have to talk about this special number right here, 6.02 times 10 to the 23rd. That is Avogadro's number, or avocado's number, if you need to remember it. 6.02 times 10 to the 23rd is an enormous unit of numbers. It is huge. There is a lot of atoms in a mole of a substance. There is a lot of molecules in a mole of a substance. When we're talking about particles, anything or any word that represents part or piece of a whole can be used with particles. So the atoms, molecules, or formula units. Okay? You have 6.02 times 10 to the 23rd, whatever small unit you want to use. So 6.02 times 10 to the 23rd atoms per mole. Okay? And then when we're talking about volume, you have this standard 22.4 liters we discussed earlier. So this is how you use the molar highway. Remember, it's very important you stay on the road. You must stay on the road. Do not deviate. Do not make your own path. Do not try to skip steps. You will go down the wrong rabbit hole. Stay on the road. Okay? Capiche? So let's talk about the mass perspectives. For us to get from here to here, we got to go through this molar mass calculation. So we got to learn how to do molar mass real quick. It's pretty straightforward and intuitive once you get used to the process. So molar mass is a gram per mole value of a compound based on its chemical composition. And chemical composition just is a fancy way of saying who's in the compound. So based on the compound, you see some average atomic masses, put them together, you have your molar mass. So the rules of the road are you break up the compound into its elements, even polyatomics. Even polyatomics. Number 2, you determine the number of atoms in each element. And step 3, find the average atomic mass of each element. That's from your periodic table. That's from your periodic table. And then number 4, you multiply the number of atoms by the average atomic mass. And then step 5, you total it all out. So you multiply across, add down. We'll see what I mean here in a second when we go through that, okay? We'll see what I mean when I go through it with you. So let's take glucose here, C6H12O6. I want to find the molar mass of that. So I'm going to step 1, break the compound down. C6H12O6. I'm going to have C, H, and O. Kind of reminds us of taking inventory, like we did when we were balancing. I see I have 6 carbons, 12 hydrogens, and 6 oxygens from this formula right here. Those are my subscripts. That's how many atoms I have. Now I gotta find the average atomic mass of each element, and that information comes from my periodic table. So right now I'm doing step 3. And in my periodic table information, literally I just took some screen grabs of the squares. I know one carbon atom weighs 12.01 atomic mass units. One hydrogen weighs 1.008 atomic mass units, or has a mass of that. And oxygen is about 16. All right. So I'm going to multiply across, add down. So if I multiply these two things together, I'll get my answer. So here we go. 6 times 12 is, not 12, 12.01. Boop, that gives me a whopping 72.06. And then 12 times 1.008 gives me like 12 and change. And 6 times 16 is 96. I've multiplied across. Now I gotta add down, or summate. That's a fancy word we can use to mean to add down. So we're gonna add these values together. This fancy sigma means summate. Or add together. So, and then you just add them together. 72.06 plus 12.096 plus 96 should give you a whopping 181, not 181, 180.156 grams. Ta-da, molar mass calculations. So what you've just told me is that in 1 mole of glucose, C6H12O6, I have 180.156 grams of glucose. These are now equivalent factors. Ta-da! Do the same thing. Same thing over here. You're going to do it again with aluminum sulfate. So I see 2 of them. I see 3 sulfurs, because here this 3 applies to that group, and this 3 applies to that one. So we're going to slide over that 3. So AlSO, 4 times 3 is 12. 1 aluminum weighs that 26.98. Sulfur is at 32.07. And oxygen is 16. Multiply across. Two times 26.98 equals that 53.96. 3 times 32.07. And 12 times 16, 190 something? 192. Now that I have that information, Summate. Adding them together, you get a whopping 342.17 grams, which tells me that in 1 mole of aluminum sulfate, I have, now that my pen changed, let me change it back. I have is equal to 342.17 grams of Al2SO4 3. Capiche? Hopefully that's making more intuitive sense now. So let's make it spicy. Let's make it spicy. Let's put this molar mass calculation principle into practice. So we're going to do some stoichiometric conversions. We're going to do some stoichiometric conversions between real-world examples. So here you have one-step and two-step problems. So in one-step stoichiometric problems, you're going from moles to your given value, moles to a given value, or moles to a given value. That's one step. In two steps, moles isn't mentioned in our problem, so we have to go through moles to get to the goal. So if my goal is to get to particles, I can't just skip over moles and go to particles for mass. I can't do that. I have to follow the road. One step, two step. So I gotta go through moles to get to my goal. Ça va? So let's start with the easy stuff. How many moles are in 25 grams of sodium chloride? Well, I see moles and I see grams here, so I know I'm gonna need my molar mass stuff, so I'm gonna just go ahead and off the jump calculate out some molar mass calculations. And from the handy dandy periodic table of elements, I'm going to grab some sodium values and chlorine values here. Oh, what is happening? Thank you kindly. Oh my goodness. Whew, there we go. All right. Anything times 1 is itself, so I'm going to just skip a step here and start to summate those values. 58.44 grams per mole of sodium chloride. All right, so that's the information I know. I started with that 25 grams of sodium chloride. Now I know I gotta get to a mole, and I just found out that for every mole of NaCl, I have 58.44 grams per mole. Now I see that my grams cancel. My grams cancel here. That goes grams of NaCl and grams of NaCl will cancel, leaving me in moles. So multiply across 25 times 1, multiply the bottom, so times that 1 imaginary 1, 58.44, divide the 2 here. I'm gonna take 25 times 1 is 25 divided by 58.44. I should get a really, really small value to how many sig figs? I see 2 sig figs here. So to report my accurate 2 sig figs, I'm going to round this value right here to 2 sig figs, 0.43 moles of NaCl. That is a final answer. Notice the final answer has a number, a unit, and a substance. number unit substance. Alrighty, friends. Excuse me. Alrighty, friends. So let's try this next one. We need to get through to how many grams are in 0.25 moles of KCl. This is a one-step stoichiometry problem because it mentions it starts in moles. So like always, we start with our given. All right. Actually, let me keep it consistent here. Really quickly. Don't like that color. Don't want that color. Why not? 25 moles of KCl. Now I need to go to grams of KCl. So I know in the grammage, I'm going to need my molar mass. So we're going to get that real quick. I'm going to squeeze it in right here. KCl, we're going to get the molar mass by using our periodic table data. I see 1 potassium and I see 1 chlorine. Now looking at my handy periodic table I have in front of me here. I'm not gonna keep switching screens for y'all since I know you know where it is now. Remember, it's that average atomic mass in the bottom of your square. Multiply across, add down. Multiplying by 1 doesn't do me any good here, so I'm going to just add straight down. 74.55 grams per mole here. So let's bring that back out. Now, I'm in moles, and I want moles to cancel, so that means for my conversion factor to be helpful, moles has to be on the bottom. So for every 1 mole of KCl, I have that 74.55 grams of KCl. That's what we just found out with our molar mass over here. Let's double check myself. How many grams of KCl we're talking about? I'm asked for grams. I'm in grams. I'm looking good to go here. Let's ditch our units. I have moles of KCl and moles of KCl that nice and neatly cancel. I'm left in grammage. All you gotta do now is 0.25 times that 74.55. And of course you divide by your bottom, but we're dividing by 1 here, so it doesn't do anything. 18.6375 grams. Remember, number unit substance, but I'm not done yet. I need to find my sig figs. This is how many sig figs, ladies and gentlemen. That's the whopping 2. So we're going to give myself 2 sig figs, so that's approximately 9 grams of KCl. Light work. And this is the same process for all of the one-step problems we're going to deal with. You're just going one-dimensional analysis or 1 unit over. Up next, you're talking about how many atoms are in 34.3 moles of calcium. All right, so I'm starting in atoms. That means I'm starting, move that out of the way. I'm starting over here. Capiche? So let's do that 1 step. I got 34.3 mole of calcium. That's FCA. Times our conversion factor here. Now, I know when I'm dealing with particles or atoms, molecules, formula units, whatever we need, we're going to have to use this fancy Avogadro's number right here. This is Avogadro's number. It is how many particles are in a mole. So no matter what particle we're talking about, we're going to be using it. So for every 1 mole of Ca. Remember, I gotta have moles on the bottom because I gotta get it to cancel. I'm gonna have 6.02 times 10 to the 23rd atoms, that's what we're given, of Ca. And then you just multiply across. It's just, however, comma, you need to keep this Avogadro's number in parentheses. Keep in those parentheses. Anytime you have scientific notation, it's a good habit to keep it in parentheses. And a fun fact for you, this Avogadro's number is a constant value. It is an established constant. It does not apply for sig figs, okay? The sig figs only come for what you are given. Sig figs come from the given. So we just do some math, multiply across the top and the bottom, divide the two, but we're dividing by 1 here, so that's not going to do nothing really for us. So I'm just going to go 34.3 times parentheses 6.02 times 10 to the 23rd. Your reference sheet gives you one more decimal than I do. My notes are established at 6.02 times 10 to the 23rd. Okay, so make sure we have that in common. So I get that whopping 2.06486, right? Yeah, 86 times 10 to the 25th. Don't write no E's. I shouldn't see E like you see on my calculator. E means times 10. But we're going to report that to the proper number of sig figs. So we're going to approximate that to I see 1, 2, 3 sig figs. So 1, 2, 3. Cut off the rest. Number, unit. Excuse me. Number, unit, substance. Boom, bow, light work. And up next, how many moles are in 3.20 liters of O2 gas? Okay, 3.02 liters of oxygen gas. All right. I'm still using my molar highway here. I'm just coming from down here at the bottom. This volume right here. You use your standard temperature and pressure constant. These two things right here are constants. These two things right here are constants we will use all the time. So we use our our gas constant here. 3.02 liters of O2. I need liters to cancel. So I know in 1 mole here, mole is my goal, so it has to go on top. I have 22.4 liters of O2. Of course, we're talking about gas. I'm in moles. That's what I'm asked for. So I'm looking to see liters of O2. Liters of O2. Okay, good. Nice, easy, breezy, beautiful. Now, multiply across the top and the bottom. And add and divide it down. So we're looking at 3.02 times 1 divided by 22.4 here. Of course, it doesn't do anything for us. So we're looking at a final answer of 0.1348. I lost it. 482. 14286. Mole of O2. Muhaha. How many sig figs we're talking? 1, 2, 3. I see 3 sig figs. Boom, boom, boom. So we're looking at around 1.35 moles of O2. Ta-da! Easy, breezy, beautiful. Now, let's do one last one just for kicks and giggles. This is like a little extra example I have found, because I can also ask you about something called formula units. Formula units is another way to say particles or atoms. So we're coming from that particle side. And in formula units, you're given that many of them. So write down your given. Formula units of sodium. Now, I know for every 1 mole of sodium, I have 6.02 times 10 to the 23rd formula units of Na. And that's just from Avogadro's number over here. And it's from this Avogadro's number, or avocado's number. That's something we use all the time. Now let's see, my goal, how many moles? Moles is my top conversion factor here. I'm good to go there. So let's see if I'm good to cancel. Formula units on top, formula units on bottom. That goes bye-bye. So all I'm looking for here is 8.428 times 10 to the 23rd. Remember, keep anything in scientific notation in parentheses. Times that one over that Avogadro's number we see. Avogadro's number. Remember, keep that in parentheses. So in your calculator, make sure to do the same. Keep it in parentheses. 428 times 10 to the 23rd divided by 6.02 times 10 to the 23rd. We should get a nice, neat number. There we go. 1.4 what? Formula units of sodium. But Mr. Cole, the sig figs don't match. Okay. Round. Ta-da. These are equivalent things, right? So just include all your extra imaginary zeros. Easy, breezy, beautiful. Those are all 1 steps. Now let's get it extra spicy and do the 2 steps. It's literally the exact same thing we have been doing, just with 1 more conversion factor involved. Because remember, when we're on these highways, when we're on this molar highway, we have to go la, di, da. You can never go la, di. That's a no-no. It's never la, di. That's a no-no. It's always la, di, da. Easy, breezy, beautiful. Now let's get it rolling. How many liters of H2 are in 5.01 grams of H2? Okay. I'm given 5.01 grams of H2. Now, I know I have to go through moles to get to liters because I'm given grams here. I'm given grams first. But my end question is how many liters. So I got to go from grams to a mole to a liter. All right, should be pretty straightforward enough. I get that molar mass value. Of H2, so there's hydrogen, I see 2 of them. Hydrogen's average atomic mass is that 1.008 we have found earlier. Multiply those together. Do bats attack people? Do not leave your iPad around your goddaughter, y'all. I'm looking for 2 times 1.008. That gives me that 2.16 grams here. And I would add the rest, multiply across, add the rest. I'm only talking about hydrogen gas here, so there's not much to go on. So we're going to keep it pushing. So I know my 1 mole of hydrogen gas contains 2.016 grams of H2. Now I am squarely sitting from my mass here. I'm right here right now. My goal is to keep going and end up here. So I do one more conversion factor. Now I know for every 1 mole of H2, I have 22.4 liters of H2 at standard temperature and pressure. That's what I'm asked for. How many liters? So let's see what cancels. Grams of H2, grams of H2, moles of H2 cancel. I see mole of H2, mole of H2. Notice I'm only canceling things that are on top and the bottom that are the same. Now what I'm left with is this liters of H2. That's what I'm asked for. So let's go run some math real quick. 5.01 times that 1 mole times 22.4. I guess my top value. My bottom value is 2.016 times 1, of course, is the same thing. Ooh, oh. Ooh. Now we do top number divided by bottom number. .666666, blah, 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 repeating. How many sig figs do I need? I need to report, I see 3 sig figs there. That's 3 sig figs. So approximately you're looking at 55.7 liters of H2. Let me just say H2 gas. Easy, breezy, beautiful. On to the next. How many grams of HNO3 are in 4.73 times 10 to the 23rd formula units of HNO3? Okay. Light work. Remember, keep scientific notation in parentheses. And formula units of HNO3 times, for every 1 mole of HNO3, I have 6.02 times 10 to the 23rd formula units of HNO3. Now that I'm in moles, I can get to grams, so I know that for every 1 gram, every 1 mole, let me get that away. So for every 1 mole, we have a certain number of grams of HNO3. And that grammage comes from its molar mass calculation, which I'm going to do off to the side over here. So for HNO3, I see 1 hydrogen. I see 1 nitrogen. And those 3 oxygens. We know the average molar mass of hydrogen. That nitrogen is going to come out at a whopping 14.01. And oxygen is going to come in at a whopping 16. Multiply across here. 3 times 16 is a good 48. Multiply across, we're gonna add or summate down. That's gonna come to 63.08018, excuse me. Beep. 0.18 grams. Let's see if I can't squeeze that in here over here. Now we just run some math. Parentheses 4.73 times 10 to the 23rd. Times that 1. Do we need to do it? No. Is it good practice? Of course. 63.018. That's the top value. Now what I got going on in the bottom, I got an imaginary 1, Avogadro's number, and another 1. So I'm going to just divide by parentheses 1 times parentheses 6.02 times 10 to the 23rd. Close up parentheses. Oh, back it up. 23rd. Over and close up parentheses. Times 1. Close parentheses. Easy. Breezy. Beautiful. Or you can do it stepwise. Just get a top number, get a bottom number, then divide it. Up to you. I prefer it that way just so I have less to key into the calculator, because without the proper use of parentheses, things can get messy and you won't know what's going wrong with your calculations. So by now I am equivalent to 49.514142871 grams. However, that is far too many numbers. My sig figs are only 3. So I'm going to leave it at 3. 49.5 grams of HNO3. Ta-da! On to the next. How many molecules are in 500 liters of helium? Okay. 500, don't forget that decimal. That decimal plays important roles in that significance. One liter of helium, I'm going from liters to moles. So I know my goal of this step is to get to moles. So for every 1 mole of helium, I have 22.4 liters of helium. Now that I'm in moles, my goal is to get to molecules. So for every 1 mole of helium, I know I have 6.02 times 10 to the 23rd MQs, or molecules of helium. That's my last conversion factor at the top. I'm in molecules. I'm asked for molecules. Let's see what cancels. Liters of helium, liters of helium. Mole of helium, mole of helium. Okay, we're good to go there. So just do some math. 500 times 1 times avocado's number, 6.02 times 10 to the 23rd. Nothing else to multiply, so I'm going to get my top value. And 22.4 times 1 is, of course, 22.4. So I sit here and divide by 22.4. So then that gets me to 1.34375 times 10 to the 25th molecules. Too many numbers. I see 3 significant figures, so I'm going to report 3 significant figures to me. All done. And that, ladies and gents, has been compound stoichiometry from all different perspectives. Your major takeaway is to, 1, keep your work nice and neat so that way you can see how things cancel out nice and easy. Figure out if it's one step or two. That will help you a lot. And stick to the highway. Stick to the highway. You do not go la D. That's a no, no. We go la D da. La D da. La di da. La di da. We do not go doop da do. That's the no, no. It's always la di da. Or same thing from down here, la di da. You must go through the mold to get to your goal. That's a two-step. You must come to the center part of being a mole. So, i.e., convert to moles first. Convert to moles first. So here's your side-by-side comparison of two-step versus one-step. They look pretty similar. The only key difference is this extra step of converting to your final piece of how many grams or whatever your question's asking you, but you're not starting in moles. So you got to get it to moles first. That's what we're doing here. We're getting this equation to put it into moles, so that way we can make even comparisons all the time. All right, and I'll keep you posted on this one. And here is some more notes for you about the rules of the road. Make sure you break them down, even the polyatomics, and use your periodic table to your benefit. These are just squares I've screenshotted off of the periodic table. Make sure you use that whole thing to your advantage always. Report what you see on my periodic table. My periodic table is a little bit older than the newer one, so the weights are probably a little off, depending on what they've researched. Now, there's the molar mass calculations. Here's your molar highway again. Just make sure you get all your parts and pieces together. And then here's the start of it with those conversion factors or those dimensional analysis. It's the fancy word for them. If you have any questions, comments, concerns, and or interjections, please feel free to reach out and email me. I'll be happy to help where I can.